Hello, my dear students. Welcome back to new classes of electrophoresis. And what is electrophoresis? Electrophoresis is the migration of charged particles or molecules in a medium under the influence of an applied electric field. The electrophoresis word that comes from Greek word means transport by electricity. The word electron refers to electron flow or current, and phoresis refers to movement. Thus, electrophoresis is the movement under electric field. Electrophoresis is generally a separation technique. Like a chromatography, it is also a separation technique and is simple, rapid, and highly sensitive technique. It is mainly used in clinical laboratories to separate charged molecules from each other in presence of an external electric field. The proteins in body fluids, proteins in erythrocytes, like hemoglobin, nucleic acids, RNA, DNA, etc. can be separated and further analyzed by electrophoresis method. Then, who is the father of electrophoresis? The scientist, Sweden scientist Arne Tiselius is known as the father of electrophoresis, and he won Nobel Prize in Chemistry in 1948 for his research on electrophoresis and adsorption analysis, especially for his discoveries concerning the complex nature of serum proteins. He used this type of a bent glass tube with the electrolyte reservoirs containing cathode and anode and a buffer containing the micromolecules that emit electrophoresis. He tested whole serum in the apparatus like this and found four distinct bands consisting of albumin and three globulin components which are named alpha, beta and gamma globulins. So for this study, he won Nobel Prize in 1948. What is the principle of a electrophoresis technique? The migration of charged particles of any size in liquid medium under the influence of an electric field. Depending on the kind of charge the molecule carry, they move towards either to cathode or anode. An ampollite becomes positively charged in acidic condition and migrate to cathode, and in alkaline medium this ampollite becomes negatively charged and migrates to anode. And what are the factors that depends on the migration of charged molecules under the applied electric field? First one is net charge. This one is net charge of molecule. Second is size and shape of particle, strength of electric field, properties of supporting medium. And the last one is temperature of the operation. This diagram we can see that this E, capital E is the applied electric field and Q is the net charge of molecule. Then the F right, that the force to the right is Q into E. Q is the charge of the molecule and capital E is the applied electric field. And F, the force to the left is equal to F U, where Small f is frictional coefficient and u is the velocity of the molecule. Then force net is equal to F is equal to ma, where m is mass and a is acceleration due to gravity. As a is equal to 0, then this F net is equal to 0, then QE is equal to FU. F right is equal to F left. That is QE is equal to FU. From this equation, we can conclude that U is equal to QE by F, where U is the velocity of the molecule, Q is charge, and E is the applied electric field, and thus this F is frictional coefficient. Then electrophoretic mobility mu is defined as the ratio of particles' velocity to strength of driving field. That is, mu is equal to U by E, velocity divided by strength of the electric field. Then we have to substitute the value of U, QE by F divided by E. Then mu is equal to Q by F, or U is equal to mu F. Now the velocity depends on particle properties. Then for the electrophoretic separation, we need a buffer. This buffer will carry applied electrical current and set up a pH at which electrophoresis is carried out. Thus, they determine the type of charge on solute, extend the ionization of solute, electrode towards which the solute will migrate, and the buffer ionic strength will determine the thickness of ionic cloud. So these are the function of buffer. Then commonly used buffer is phosphate buffer, and its pH value, depending on the pH value, there are the different kinds of buffers that we are using. Around 7 pH, we are using phosphate buffer. That's the neutral pH we are using phosphate, and electrosporate TDTA, TBE buffer around 8, like that. Lithium borate buffer is around 8.6 pH. These are the commonly used buffers for electrophoretic separation. Then the supporting medium. For zone electrophoresis, we need a supporting medium for electrophoretic separation. Supporting medium is a matrix in which separation takes place either on slab or capillary form. Example: starch gel, cellulose acetate, agarose, polyacrylamide, or paper, etc. They are mainly used as a supporting medium for electrophoretic separation. And what are the factors affecting electrophoresis methods? The rate of migration or the separation of particles during electrophoresis will depend on following factors: the sample, the electric field, the medium, and the buffer. The charge, size, and shape of the particle will depend on will affect electrophoresis method. Charge, size, and shape of the sample molecules or arranged molecule will affect electrophoresis separation. Next is the electric field. The rate of migration under unit potential gradient is referred to as mobility of the ion. An increase in potential grade increases the rate of migration. Now, the amount of applied electric field increases, it will also affect the mobility of the ion. Then the medium. We can use inert medium for this electrophoretic separation. The inert medium can exert adsorption and molecular saving effects on particles, influencing its rate of migration. By two methods, by adsorption and by molecular seeding, will affect the rate of migration. And the last one is the buffer. The buffer can affect electrophoretic mobility of the sample in various ways. The buffer composition, pH, and ionic strength. Then next is the classification of electrophoresis. Electrophoresis is working on basic principle of migration of charged particles under the influence of an electric field. So based on the supporting medium used or stabilizing media used, electrophoresis can broadly divided into free electrophoresis or electrophoresis without stabilizing media. The other classification of electrophoresis is zone electrophoresis or electrophoresis in stabilizing media or supporting media. First, you have to discuss about the free solution electrophoresis. In this electrophoresis, stabilizing media or supporting media is not used. Free solution electrophoresis is again classified into five types: moving boundary electrophoresis, free flow electrophoresis, third one is micro electrophoresis, fourth one is capillary electrophoresis, and the last one is microchip electrophoresis. These are the classification of free solution electrophoresis. That this type of electrophoresis will not require any supporting medium or stabilizing media for the separation. So the free solution electrophoresis, first one is a moving boundary electrophoresis. It's otherwise known as free boundary electrophoresis. This is a type of free solution electrophoresis that it does not require a stabilizing media or supporting media for its separation. This technique is developed by Arne Thesiles in 1937. He is the father of electrophoresis. This apparatus consists of a U-shaped cell filled with a buffer solution and electrodes immersed in these buffers. The motion of charged particles through the stationary liquid under the influence of an electric field takes place. A sample applied could be any mixture of charged components like a protein mixtures. On applying voltage, the compounds will migrate to anode or cathode depending on their charges. So this is a diagram of moving boundary electrophoresis. This consists of a U-shaped cell and containing anode and cathode electrodes, and buffers are also filled in these containers. U-shaped cells. Then the samples are taken in this container. Depending on the charge of the molecules, the particles may move either to the anode or cathode depending on the charge. This is sample mixture containing this A minus, B plus and C plus charges. And after electrophoresis, move the negative ions move to anode and the pure positive ions move to cathode. This is the after the electrophoresis separation, the particles move with respect to their charges. This is the moving boundary electrophoresis. This is developed by Arne Thesiles, who is the father of electrophoresis. Two parallel plates, a back plate and a front plate, flows under laminar conditions perpendicular to the electric field. This is the diagram. The sample Introduction or buffer flows perpendicular to the electric field. The buffer flows perpendicular to the electric field. And here two glass plates. Between these two glass plate, the sample and the buffer flows. This is a front glass plate and a back glass plate. And the buffer flow is between these two plates perpendicular to the applied voltage. The buffer flow is perpendicular to the applied voltage. Here, the distance between front and back plate can be adjusted by spacers and is usually between 0.51 to 0.5 mm. And the platinum wires are used as electrodes. The distance between these two glass plates can be adjusted by using spacers. The distance of the gap between these two plates, front plate and back plate, is between 0.1 and 0.5 mm. And what is made of these plates? The backplate is usually consists of a cooled aluminum block covered with a plastic covered glass mirror. The backplate is made of cooled aluminum block covered with a plastic covered glass mirror. And the front plate is nowadays made of PMMA. It's otherwise known as polymethyl methacrylate, also known as acrylic glass or simply acrylic. And the voltage or external electric field is applied perpendicular to laminar flow of a buffer. The analytes in the laminar flow can be separated by charge or its isoelectric point. To one end, the sample is injected at a definite spot, and at the other end, other fractions are collected through an array of tubes, which leads to a 96 well microjitter plate. This is a continuous electrophoretic separation method. Besides the separation of soluble substances, this technique is also used for identification, purification, and isolation of cell organelles and membranes or whole cells such as erythrocytes, leukocytes, tissue cells, and also the agent of malaria and parasites. This method very effective since even minimal differences in the surface charge of particles and cells can be used for separation. This is sample injection probe. There are several ways for the separation of these samples depending on its charge. Buffer flow and sample introduction are like a perpendicular to the electric field. Here we can collect the fractions after electrophoretic separation. Next is microelectrophoresis. It involves the observation of motion of charged particles or small particles in an electric field with the help of a microscope. Microelectrophoresis is consists of a microscope for viewing the motion of the particles, movement of the particles under the electric field. In modern days, this microelectrophoresis is mainly used for measuring the theta potentials of cells such as RBCs, neutrophils, bacteria, etc. So, the theta potential which determines the stability of a medium. Theta potential force below a certain level, the colloid will aggregate due to attractive forces. Also, high theta potential maintains a stable system. Theta potential is a surface charge property. The apparatus for this microelectrophoresis consists of a capillary cells, two distinct chambers that include electrodes and a means of observing the motion of particles. So, this is the apparatus for microelectrophoresis. Two containers for these buffers, and also electrodes are immersed in it at anode and cathode. And there is a small capillary also And this is a microscope for viewing the motion charged particles, thus determining the zeta potential of the particle. The apparatus is filled with a very dilute suspension and the chambers are closed. A direct current voltage is applied between electrodes in the respective chambers, and we can determine the zeta potential and also the velocity of the particles by viewing the movement of particles under the influence of electric field. By making reasonable assumptions about the size of the observed particles and the electrical conductivity, it is possible to calculate the value of zeta potential. Zeta potential values near to zero indicate that the particles in the mixture are likely to stick together when they collide, unless they also are stabilized by non-electrical factors. Next is capillary electrophoresis. Capillary electrophoresis is also known as free solution capillary electrophoresis. Capillary electrophoresis is a separation technique in which charged species are separated based on charge and size by their different nature of migration in the electric field. So this capillary electrophoresis is otherwise known as free solution capillary electrophoresis. This capillary is usually made of negatively charged fused silica inner wall, which forms an electrical double layer with the cations in the running buffer. These cations in the electrical double layer move towards the negative cathode, and hence the overall direction of flow is also known as electroosmotic movement towards the cathode. So the capillary is made of negatively charged fused silica inner wall. This is a simplified diagram of capillary electrophoresis. Here we can say that two buffer reservoirs, one for catholyte and other for anolytes. Then electrodes are immersed, anode and cathode are immersed in it. There is also a power supply. Then this is the capillary tube which is made of negatively charged fused silica inner walls. Used for the for the detection of these analytes, uh, there is a detector and system for data collection also. This is a simplified diagram of capillary electrophoresis. A mixture in a solution can be separated into its individual components quickly and easily by capillary electrophoresis. The separation is based on differences in electrophoretic mobility. This is directly proportional to the charge on the molecule and inversely proportional to viscosity of the solvent and the radius of the mat. The velocity at which ion moves is directly proportional to the electrophoretic mobility and the magnitude of applied electric field. This technique is mainly used for analytical and micropreparative electrophoresis. Usually the separation is carried out in a fused silica capillary tube 20 to 30 centimeter long with an internal diameter about 550 to 100 micrometer. The silica capillary tube pressure 20 to 30 centimeter length and internal diameter of about 50 to 100 micrometer. Then sample injection. Sample injection is accomplished by temporarily replacing one of the buffer reservoirs with the sample reservoir. For the sample injection to the capillary, we are temporarily replacing one of the buffer reservoir, either of the catholyte or of the anolyte, and temporary replacement with the sample reservoir. A specific amount of sample is introduced by controlling either the injection voltage or the injection pressure. Both ends of the capillary are immersed in a buffer container into which the electrodes are immersed. Used silica capillaries are otherwise used in cast chromatography. The amount of chemicals and sample needed is very low. The volume of injected material is usually not more than 2 to 4 nanoliter. So nanograms of sample material is only required. This is one of the advantage of this capillary electrophoresis. The power that can yield voltage up to 30 kilovolt is required. Joule heat can be dissipated very effectively from these thin capillaries with the help of a fan. Capillary electrophoresis separation typically takes about 10 to 20 minutes. There are many detection methods possible: UV visible, fluorescence, conductivity, electrochemistry, and so on. In most applications, the fractions are detected by UV measurement at 280 and 260 nanometer. Next is microchip electrophoresis. Actually, it is a miniatured form of capillary electrophoresis in a planar device, usually in the shape of a cross. The cross size of 1 to 10 centimeter and have a diameter of about 50 micrometer. And this sampling application and separation is done via narrow channels which have been introduced into the surface of a glass, silicone or polymer material by photolithographic effect. And one of the advantage of this miniature form of capillary electrophoresis, that is microchip, is the sample requirement is very low. Usually 1/10 of that of capillary electrophoresis is required. So it's a miniature form of capillary. All the reservoirs are equipped with the electrodes for sample and buffers. This is the miniature form of capillary electrophoresis arranged in the shape of a cross. The simplified diagram of this microchip electrophoresis. There is a sample reservoir, sample waste reservoir, a buffer reservoir and a buffer waste reservoir. And the portion marked is the sample separation point. And